Free now. All right, got people online. All right, well, today is a real special treat, okay? Where we have a group of people who have been over at the NOAA building for a long time, still are there, okay? But are now affiliates of NSIDC, right? This has been an effort we've been working on for quite some time because there's a natural partnership here between what we do over here with all the data management we do in the cryosphere and all the research we do in the cryosphere and what's been happening over there in the SCAGS building. So we're going to have a talk today, and it's going to be with Matthew Shupe over here, Ola Persson, who I've known for many, many years, of course, in math as well, right? Amy Solomon, right? Michael Gallagher and Sledd and Bill Neff, who I've also known for many years, right, as a series fellow. And we're really going to learn today about Arctic processes and the many observational and modeling tools that are being used to study these physical processes in the Arctic system. Everyone who's presenting here has just huge experience in doing Arctic research, being Arctic research. Of course, Matthew, of course, he was lead scientist on the Mosaic effort. Ola, I mean, we've had many discussions on Arctic energy budgets and things like that, you know. It's great to see it. Of course, I've known Bill for many years. So really, we're really strengthening our science here, right? We're strengthening our science with this collaboration that we've got going on now, and we really want to build it. And this talk is our first step. So without further ado, I believe, Matthew, you'll start out. So you have the electronic podium.
Actually, if I could add one thing.
Add one thing.
Okay, it's many years ago.
Yeah.
Mark, Marika Holland, I, and who else was there? Met with Tony Stefan.
Tony was there, yeah.
And Tony was interested in heading up a virtual polar research center in Boulder.
Yeah.
And he tried to go to the dean and get a senior level faculty position and lead such a virtual effort. But the dean wouldn't give it to him. So
Deans do this.
So 20 years later,
Here we are. We're starting to come together in this new world. So this is just really exciting for me. I'm just thrilled. So here we go. Take it away.
Thanks, Mark. Great to see everybody here and online. Yeah, Mark gave a great introduction to us. So, title here is Observing and Modeling Arctic System Processes. You'll kind of get a flavor of some of the work we do. It's going to be really broad brush. So we're kind of an Arctic processes team, and Mark already gave this slide. So I don't really need to give it, but one of our big goals is to really strengthen some of the connections in Boulder here. And we're all six of us are series employees, so we're all like the rest of you. And so we really want to build some of the connections, and we want to kind of increase our footprint on campus in addition to NOAA and build a lot of those bridges. So this is our introduction to our team. So there's a lot of obvious links between the kind of stuff we do and the stuff that NSIDC does. So we're very interested in Arctic system processes. So we've done a lot of studies to understand things like sea ice extent and properties, the Greenland Ice Sheet and its evolution, the atmospheric drivers of the cryosphere, themes like that. We've developed a lot of modeling tools to advance our understanding of processes, and of course, sitting over at NOAA as well, it's a lot about forecasting, right? How we forecast the Arctic system and how does that affect the rest of the globe. And then we also do a lot of outreach and communication activities, and I know you all do as well. So those are some of the nice links that we share. So today we're going to have kind of a group seminar. There's 6 of us. We're going to do a little hand it around, and everybody's going to give a little like 5-minute intro to who they are, the kind of work they do. And most of this is kind of the current work that we do. We're not going to dive too much into the history of that. And team, we each have 5 minutes. Right? I know it's a challenge for some of us to speak in 5-minute increments, but we'll do that. And I'll ask, so we certainly are open for questions, but let's do the questions collectively at the end, just to kind of help with the flow of things. So other than that, we'll start with, and I kind of listed the order that we're going to go in. We'll first start to hear about some Greenland kind of things, and we'll move into some modeling and towards some energy budget kind of work. That's kind of how I organized it thematically. So we'll dive right in with Michael Gallagher. And I'll drive here, so just say next slide and we'll progress that way.
Yeah, might as well get up there just so people can hear.
Oh, yeah.
Yeah,
Sounds good.
stand up at the front that way. It's just a little easier. Is that, Miss Stia, can you hear everyone okay? Or whoever's, Twyla, can you hear everyone okay?
Yeah, I can hear everyone.
Okay, good. All right, all right.
And the mic's right.
Yeah, we have the, what do you call it? That owl.
The owl.
The owl.
Ornithopter. Perfect. Looks like I get to go first. My name is Michael Gallagher. Been sitting at NOAA for a decent chunk of time. In this precise moment, a lot of my effort is going towards working on observational platforms, and one that's sitting in the parking lot just west of the building out by the buses. We've got, as a gang, a large set of 4 parking lots, and we've got a whole bunch of instrumentation there. Have we set a time for, we talked about it? We welcome visitors. We might set a time to get folks out there to actually look at it, and I'll show some photos there. I split it into 2 things: the science, the research topics, the papers I'm interested in writing, and then my broader goals for my work. In the broader goals for my work, I'd love to build better in situ observation platforms that can serve my specific science research topics. And I've been pushing really hard in that direction. I'm giving a few specific points. Real-time data transmission from the observation platform so that modelers can evaluate their forecasts and climate models in real time so that they can do forecast validation. Autonomous operations so that we don't necessarily have to have full-time staff operating these in places like Greenland where that can be really hard. And ideally you measure the fully coupled climate system. So you get profiles from as high up as you can go all the way down to the subsurface to connect everything. And on those platforms, I'm interested in getting a bunch of the key climate and cryosphere climate measurements that a lot of you were probably interested in. So energy budget in the atmosphere and its connection to the subsurface response to that energy budget. And then vertical atmospheric profiling, because the energy budget, we all know, is controlled by a lot of what's happening near the surface and quite a bit further above, and clouds and more that are tied to that. I've written a few papers on Greenland melt event characteristics, so synoptic evolution, those kinds of things. I have a figure related to that. I'm working on, if I get the time for it, to wrap up a paper on turbulent energy exchange that was using measurements from the Mosaic expedition and its connections to surface topography. I'm really interested in evaluating bulk algorithms because not all measurements are super detailed, and it'd be really great to get better bulk algorithms for retrieving energy budget. In kind of my high level stuff, I have a nice little buzzword there: machine learning. Sensor fusion and combined retrieval from observations is somewhere I'm interested in pushing. So you have these measurements, but combining them in clever ways, you can get better research done, and more buzzwords there. Next slide. But most of my idea is to show a few pretty pictures. This is what's sitting out in the parking lot out by the buses. So all of this is just out there. The top right is the container. You can see the nice crane that the folks have right next door. A bunch of solar panels. There's solar panels on top of the container. We're taking this to Greenland in a little less than 6 weeks, I think. And we've constructed it there. It's a combined thing. There's one side of it, it's the science platform. This is the sled with the skis there, and it's got a whole bunch of measurements, 60 something sensors on it. And then the thing on the right is this large power system that we built to enable this. So there's 20 lithium batteries there, lithium being something that should worry most people if they hear that, and there's been a bunch of effort put in that. We're taking, I think, 16 solar panels, 4 wind turbines to do fully renewable, so no diesel backup, and that's a thing too we can talk about. But next slide. These are some photos. So I think I saw Twyla ask a question in the chat. Is it Summit Station? That's going to Raven, and it's going to operate. We'll install it for a month. It'll operate autonomously till the end of the year. These are a few photos from Summit Station, just to say that we have ties to a lot of the research done there and measurements. This is another set of observations that I worked closely on with our colleague at NOAA, Chris Cox. It was a buoy that was put out by the University of Washington in collaboration with the Navy and our Navy Research Lab, ONRL, and we did a fully coupled set of measurements there. Not much, well, no atmospheric profiling, but all the way through to the ocean, and then freezing up and capturing freeze up and melt in the Beaufort, which is really interesting. Hopefully, paper incoming at the end of the year there. Next slide. This is just a quick plot, because I'm a scientist and I'm obligated to show a plot. This is from Summit Station with the sled last year. So we were testing, trialing a lot of that instrumentation. Top is just the temperature variability. This is during the transition in May, when we went from the atmosphere being mostly colder than the subsurface to being mostly warmer than the subsurface. The bottom section is from a thermistor string, and you can watch the variability of the atmosphere go positive, and then that gradient remain constant into June. And next slide. Nope. We're gonna transition to Greenland melt drivers. This will just be a little blurb. I worked quite a bit, now seemingly a long time ago, this was published 4 years ago, about the time evolution of drivers of melt in Greenland. And these are some self-organizing maps. Doesn't matter so much, but the conclusion was that clouds and warming events co-vary in time on daily time scales in Greenland. And I did a whole bunch of detailed work on that, but I'm really interested in the future in taking this research and going about time evolution. So you have daily events, but how are those all interconnected and how do we move through those? And that's the last one.
So we'll move on to Bill, keep it in Greenland.
No, no, Antarctica, where is it? Yeah, so I got started with looking at atmospheric rivers affecting Greenland with the big melt in 2012. Before that, I spent most of my polar research time in Antarctica. I did my PhD there back in the 70s, in the dark ages. I started in NOAA before NOAA was NOAA, so I've been around for a while. But anyhow, just before I retired as a lab director at NOAA, we had people in the lab studying atmospheric rivers. We had people working on Greenland, and I decided it's time for me to become bipolar. There's medication for it, I know, but you know, I haven't taken it yet. So anyhow, but the interesting thing in Greenland is Kyle McInerney did this article looking at these atmospheric rivers, and a lot of people were interested in atmospheric rivers because they were long, they were violent, they drowned California, and so forth. And we looked at the melt event in 2012, and I said, that's an atmospheric river. And turned out, in fact, that's what brought the moisture to Greenland. Started in a heat wave in the Midwest, went over the ocean, picked up moisture, went to Greenland, and then formed this thin layer of clouds that modulated the surface energy budget, and Greenland melted. Next one. So I said, well, I don't want to learn Python to do this river analysis, so I'm going to find something simple to detect atmospheric rivers. So I was looking at reanalysis data and discovering that there's a systematic transport along the coast of Greenland, and I said, okay, time to do a point analysis. So I did. I looked at the distributions of total integrated water vapor in the total column versus wind speed versus direction, discovered that if you go up toward the Baffin Bay, that is very focused and controlled right by the topography. I said, well, I can characterize the entire atmospheric river with 1 point from the reanalysis data. So I picked 850 hectopascals and over Davis Strait here and said, what can I do with that? Next slide. And so I said, okay, we have these melt maps, and we have all the digital data from Thomas Mote from 2000 through 2022. And I looked at data in particular from 65 north over at Baffin Bay, and I restricted the wind direction from coming from the south. I did correlations there between integrated water vapor and temperature. Oh, hey, it's well correlated between temperature and melt fraction in this little box over here on the coast. That was well correlated. And I said, well, basically it's warm. There's moisture coming from the south, and it's melting Greenland. Next slide. And so we were able to go through and look for all cases where the wind was from the south, it was warm, and so forth. And then we did this composite analysis on about 20% of the observations were atmospheric river events. And you can see this characteristic pattern with the low pressure, the ridge, which matches Mike's SOM analysis for the maximum temperature and moisture deposition at Summit Station, I almost at South Pole. You can tell, you can see the atmospheric river coming up here. Omega sinking on this side of the ice sheet, subsidence over northeastern Greenland. Then I looked at strong ARs detected only by virtue of high melt on the coast. So I'm only looking at this where there was no more than 90% melt in that little box along the coast. And we get the same pattern. So basically, the melt on the coast, this ridge trough pattern are all well correlated. Next slide. And so then I said, okay, what's a seasonal behavior? Because this is Kyle Mattingly had published this paper, arguing atmospheric rivers, part of this ridge trough pattern would descend with a Foehn effect in northeastern Greenland. And he was arguing that that was destabilizing the glaciers in northeastern Greenland and massive sea level rise, drown Mar-a-Lago tomorrow. Okay, and was that really a Foehn effect, or was it just, it was getting warmer? Well, it turns out the warmest period in Denmarkshaven over here is on July 22nd, which is the case that Kyle highlighted in his paper. And it was 44 degrees Fahrenheit. So anyhow, so I said, okay, well, let's see how it behaves seasonally across each of these stations. So we looked at West Coast, sort of just, well behaved, melts most into summer. The Northeast Coast peaks a bit earlier, and that's at 50% average. Dive/Raven, you can see, in fact, where the melt peaks there with an average of 0.4 of the pixel of the box with melt pixels. The total Greenland ice sheet looks here and peaks in midsummer also. So next slide. Now, the interesting thing is I asked, well, can we go back in time further? So I was playing with the 20th century reanalysis for the 2014 paper on the Greenland melt event. And so I went back and looked at the frequency of atmospheric rivers during the summer on the west coast of Greenland using 20th century reanalysis, and then compared more recently with the Era 5. And guess what? The 20th century reanalysis actually captures much of the behavior of atmospheric rivers affecting Greenland going back in time. And you see this increase back in the late 20s, early 30s. Turns out William Saint-Amand analyzed the ice core from the Neem site and discovered, in fact, there was excess accumulation and excess temperatures from delta oxygen 18 in that ice core during that period when we had more atmospheric rivers. So it allows us to go back in time and look what's happened in Greenland over the last 100 years, basically. So fun stuff.
Great. All right. Cool. Next, we'll move on to Amy Solomon. Looking at some modeling work.
Okay, so I'm the modeler of this team, and one of the main emphasis of the work I've been doing is to advance process understanding of the formation and maintenance of Arctic clouds. And the motivation for this work is shown here on the left. This is a paper from Pippen and Rotson in 2014. It's showing the joint PDFs of the surface net long wave radiation and low level stability. And these two figures are from observation, so from Barrow on the upper figure and Shupe on the lower figure. And this is just to highlight that typically we find this bimodal distribution with a clear sky and a cloudy sky mode. But on the right here, this is just three from the CMIP3 intercomparison, 3 models. So CCSM4 on the top, GFD on the middle, just to highlight that in general, models cannot simulate the cloudy mode. So they're not simulating the clouds in the Arctic. And so we want to understand why. What are the processes that they're missing? And so one really interesting study, so these are from 2 LES studies that I've done. The middle one is because there's always been this disconnect between how many aerosols form ice in clouds and how much ice is observed. And it's really been this conundrum that people have been trying to understand. And so one thing we wanted to look at is how important is recycling of IMP? So IMP are the aerosols that form ice in clouds. And so recycling means that as the ice falls out of the cloud and sublimates, the aerosols be released and then they can be mixed back up into the cloud by turbulence. And in general, models do not include this process. And so we wanted to understand, is this playing an important role in maintaining the phase partitioning between ice and liquid in the clouds. And so in the upper right, this is showing a time series of ice water path in red and liquid water path in black. And the dashed line is for without recycling and the solid line is with recycling. This is just to show that when you do allow for this process, you can maintain the phase partitioning between liquid and ice in these clouds. And so I did, this is a single layer mixed phase stratocumulus. That's what I've been focusing on. On the right, so we've been looking at the role of CCN versus IMP. So CCN being the aerosols that form cloud droplets versus the aerosols that form ice. And so this is really interesting because CCN are orders of magnitude larger than IMP. There are very few IMP in available to form ice. And so what we're looking at in the column on the left is what happens when you increase and decrease CCN by a factor of 2. And so the blue line shows that when you increase the CCN by a factor of 2, this top row is just liquid water path. So you're increasing the amount of liquid water in the clouds. And on the right, this is when you increase both IMP and CCN by a factor of 2, and you get the opposite result. So even though IMPs are orders of magnitude smaller than CCN, if you increase it by a factor of 2, you actually reduce the liquid in the clouds. So these are just some of the processes that we've been looking at, focusing on the LES scales. Next slide. My other role is to evaluate simulations of Arctic surface atmospheric cloud systems with campaign data. And so these are just 2 examples using observations from Mosaic. So on the left here, this is a diagnostic that we really like to use because it's telling us directly about parameterizations for the sensible heat flux. And so this is showing, these are just scatter plots. So sensible heat flux divided by wind speed on the y-axis and near surface stratification on the x-axis. And these are the observations. So there are 4 lines here because we have 4 different sites. It's called the distributed network. And so what's really interesting is when you get very stably stratified environments, basically the turbulence shuts off. And what these are 7 state-of-the-art models. So this is the model that we developed. They'll talk about it in a minute, called CAPS. This is the French forecast system. This is the ECMWF, Russia, the Navy, the German Weather Service, and this is from Norway. So just showing that even now, so this is showing, so these solid lines, the straight slope here means that there's a constant transfer coefficient. And so when you're having more stratification, stably stratified environments, we're getting larger sensible heat fluxes, which is clearly not observed. And on the right, this is just showing, this is from the overview paper by Ben Robb that was just published. It's showing the surface skin temperature in the upper figure, and this is just wintertime for these 2. And in the lower figure is showing the ice surface temperature. What's really interesting here is that the biases, so the observations are shown in black in these. The biases, there's sort of a scatter for the surface sensible skin temperature, but you can see these large biases in the ice surface temperature. And that's because of the way the different models are treating snow and ice. So this is just showing how important it is in terms of the growth of the sea ice and the impacts with the ocean on the way snow and sea ice are treated in the models. Next. These are just some of the current projects that I'm working on. So in collaboration with ULA, we're looking at the impact of an Arctic cyclone on the sea ice and the ocean using this CAPS model, which I'll talk about in a second. And so I've been working with trying to improve the simulation of Arctic clouds in the UFS. And it's just such a complicated system that I've developed this test bed where we run LES for very idealized stratocumulus case, but we allow coupling with aerosols. And we run exactly the same idealized framework, but for weather scales to really evaluate the parameterizations of turbulence, microphysics, and their interactions, as well as their interactions with aerosols. I'm developing cases for Mosaic that will be included in the CCPP single column framework. That's what they use with the UFS for NCAR to develop parameterizations. And so as to allow the scientific community to evaluate and develop parameterizations specific to the Arctic. So 1 case for mixed phase clouds and 1 case for very stably stratified environments. I'm leading the forecasting for an upcoming campaign, the NASA ARC6 campaign. And I'll talk about that in a minute. And just one thing I wanted to say. So I've been chairing the Click-Clybourne Northern Oceans Region Panel for the past 6 years, and I'm stepping down because I have to. But I just wanted to say that we're organizing this really interesting summer school and workshop. And it's in coordination with the Southern Ocean Panel. So we were working with the Southern Ocean Panel for a workshop last year, and it was so insightful for people from the north to understand how the polar system in the south the processes and how they interact. We're focusing on freshwater fluxes, but we found it to be very insightful. So we're working together again. And we're going to be having a workshop on the role of sea ice and its variability in the climate system. So I encourage everyone to participate in that. Next. So I just want to say a little bit about the CAPS model because we've been using it for process studies, for forecast products, and it's been a really big part of our team for a number of years. And so it was developed from the RASM model, which John Casano played a very large role in, which was developed from CESM. And we run it every day. It's initialized with the GFS, AMSR2, and the NOAA SST. And we run it for 10 days. We provide, this is a snapshot of the webpage. But we provide different forecast products to the public, as well as model output in NSIDC format every single day. And we also have specific special request products, depending on what campaign we're supporting. So for this campaign that I'm involved with, ARC-6, it's been very interesting because since it's a NASA campaign, we're interested in the satellite retrievals. So I'm working with a student here at CU who's looking at the thin clouds that are not observed by the satellite and trying to figure out how we can improve the algorithms. And so we have these specialized products of like cloud top temperature and cloud top height and things that he can use to see to what extent the satellite retrievals are not capturing the clouds. And we have evolution of ice flow. So we have a few buoys we'll be placing north of Greenland. I've already developed these products so that we can forecast the ice drift and then the atmospheric variability above it. And so it's going to be really important to look at precipitation events, how it changes the properties of the snow and the ice, and we can track that in time, as well as evaluate the forecast.
Good question.
Okay. And also cloud evolution. So a big part of this campaign is to get observations of turbulence and microphysics at the same time in the clouds. And that's going to be incredibly powerful to be able, because these LESs that I'm using are still models. And so I need to be able to evaluate them with these coincident dynamics and thermodynamics and microphysics in the cloud, which is what we hope to get. And I'm using this model to forecast where we should be flying. So that's
Great, thanks, Amy. Next we'll move on to Anne, who will do a little bit of model stuff and dive into some energy budgets.
Great, so I am currently a postdoc working with Matt and Amy for the last couple of years. Most broadly, I'm interested in the Arctic change or Arctic changes happening in the Arctic and its variability, and I've been studying that using the energy budget as a framework. So during my PhD, I use satellite observations and global climate models, largely focused on the top of the atmosphere. But in my postdoc, I've come down to the surface and I'm studying the surface energy budget, which is what I'll be focused on for the next probably 4 minutes. So in my postdoc, I've gotten to use observations from Mosaic, which I'm sure many of you are familiar with. It was the drifting campaign from 2019 to 2020. And the first question that I came up against in my postdoc was estimating the snow thermal conductivity from Mosaic. And so you need the thermal conductivity in order to get conductive fluxes, which are important in winter to balance the atmospheric fluxes. And so to do that, I've used sea ice mass balance buoys. So there's an example of one here in the Mosaic flow. Next. And these buoys give profiles of temperature. So they're installed vertically and you get temperature from the ocean through the ice, snow, and up to the atmosphere. And that's shown up top. And then of course, this temperature is going to vary. So we can see it varying in time as well as vertically. And those changes, both vertically and temporally, are going to depend on the properties of the ice and snow. And so using these changes and assuming only vertical heat transfer, next, you can back out the properties that influence these changes. So the thermal conductivity that I was originally interested in, as well as the density. And so you can see these profiles in time from a buoy. And it's kind of this interesting view that you get of the subsurface, whereas a lot of other measurements are kind of points that are discrete in time. So next slide. And so with the thermal conductivity, same plot shown here, you can combine it with the vertical temperature gradient and actually get an estimate of the conductive heat flux. And so that's shown here from one of the buoys over the Mosaic winter. Next slide. And then we can come back to the surface energy budget and start looking at its variability. So in these bottom two panels, we have fluxes. In panel C, it's the atmospheric fluxes, radiation and turbulence. And then in panel D, the pink lines are estimates of the near surface conductive flux from all the different buoys. And so there's some spatial variability. We have a bunch of different sites included here. There's also a lot of temporal variability that you can see. And that's related to what's happening in the atmosphere. So on top, we have radar reflectivity indicating clouds. We have skin temperature, wind speed, and we can see those variations are related to what's happening in the fluxes. And so a lot of what I'm still working on is relating that variability to the environment and with specific focus on comparing two models. Next. And so that's a lot of what I've been doing now is using process diagnostics to evaluate weather forecast models. So shown here, it's cut off. In purple is the observations, in teal is IFS, the operational forecast model from ECMWF. And I've shown regressions between fluxes that respond to temperature and then the incoming radiation. And this is just winter, so it's downwelling enclave. And the slope of that regression represents the response of fluxes to radiation. So it kind of answers the question, if you have an excess of energy coming into the surface, how does it get partitioned against the other surface energy budgets? And so the slope of that line gives us a nice metric to compare with forecast models to see if they're getting those processes and those relationships right. If they are, what is the model doing well? And if they're not, what's driving the difference? So that's some ongoing work that I'm still doing.
Thanks, Anne. Now we'll move on to Ulla with a variety of processes.
Hi, so I'm Ulla Persson. I've done article-related studies since 1977, so a little bit of history there. Okay, okay. So what I typically have done for the article-related studies I've been doing, I've been looking at these understanding the roles of different processes through the measuring and modeling of them, and the key relationships behind that picture there. And so two examples here of these equations showing these relationships are given here. One is the equation of motion for sea ice. So where we have the changes in ice velocity is forced by a number of terms. In particular, what came on is really important is the atmospheric stress, but also the internal ice stress tensor and the ocean stress also plays a significant role at times. And so we're exploring those relationships there. Interestingly, if you take the divergence of that first equation, you actually get the second equation there showing that the changes in ice divergence, which is really important for opening and closing of leads and those kind of things, is related to the atmospheric divergence and spatial gradients or surface drag coefficients. So that kind of shows us what kind of processes we should be looking at in the real world to address these different relationships. Also, the surface energy budget has been mentioned several times, and so we often break it up into the downwelling, upwelling, short wave, and long wave radiation, and the turbulent, sensible, and latent heat fluxes. Next. So, using that first isometric equation as a background or motivation, we've done a study here on the impacts of a midwinter Arctic cyclone on the dynamic air-ice-ocean interactions during Mosaic. So this is a February 1st case of 2020. And so what we see, we have passage of a low pressure center over the Mosaic site. It had looked like from the soundings, a low level jet in the warm sector and one right behind the cold front here. And what we see is that this low level jet behind the cold front and the cold front passage really was an important component in the air ice ocean interaction. So we have very strong temperature drop with that cold front. strong surface winds because of this backside low-level jet, and strong change in the wind direction, and importantly, very large increase in surface stress, the air ice stress. The bottom panel shows in red here, the atmospheric divergence showing convergence with the cold front and also with the warm front, as one would expect. But from a number of GPS ice buoys, we can also calculate, for instance, the ice divergence, which is this blue line, showing ice convergence also with that cold front. And generally, shearing in the ice throughout the entire passage of this low pressure center. Upper right here, now looking at, we had about over 50 of these GPS buoys scattered around the mosaic site. And so we can group them into subgroups then, and then calculate, for instance, deformation things in the ice. So divergence, shear, or vorticity, locally for that subgroup of buoys. And what we see is that, if you want to, one more, see that for these subgroups, when this low-level jet, so these green lines here are the ice attacks at 925 hectopascal, so correspond to this low-level jet behind the cold front. When the core, that low-level jet comes over one of these subgroups, we get peaks in some of this deformation. So divergence seems to be labeled that low-level jet, as does the shearing. So that's looking at kind of the response of the ice to the atmospheric forcing. Go ahead. And then we'll also look at the upper ocean. And we have, here's this maximum in stress behind the cold front, underneath this low-level jet here. In the upper ocean, just below the ice, at 5 meters, we have a peak again of the ocean turbulence, the ocean stress between the ocean and the ice. And we see that it produces a shearing, strong shearing in upper 10, 12 meters of the ocean. And we also see evidence of mixing in the upper ocean from this one event down to this mixing layer, 20 to 25 meters down into the upper ocean. This is higher or shallower than the actual mixed layer, which is more of a seasonal type of determined layer in the upper ocean. So we're looking at these air ice ocean interactions. In this paper that we just submitted, this is observations. We're looking at the modeling of these interactions as well in CAFS and in IFS. Right, next. If we apply that sort of energy budget equation, we can look at things like autumn freeze-up mosaic, which we have started doing. So this shows 5 images from the leg 5 of mosaic, showing that we have very large amounts of melt ponds when we first arrived. Go ahead. And that these melt ponds froze up with one more. Froze up a little differently, like in the red circle here. Clearly some melt ponds froze up between the first 2 images, while in the blue circle, they didn't. And so the bottom line is that the freeze up was very heterogeneous, and spatially and temporally varying. Wait, next. And we can also look at from the some other parameters. So we see that in the atmosphere, there's temperature in the lower portion of the atmosphere, and with the blue lines being a 0-degree isotherm. And so you see going away. What next? We have above freezing air. We have enhanced net radiation and downward sensible heat flux that produces a positive value of this net atmospheric energy flux. That's when we have our melt. So when we first arrived, we primarily had melt with a few little episodes of freeze going on. But then later on, we had general freeze with one last little melt period associated with a cyclone. So next. And so, or look at it the other way around, saying that this is kind of the gradual change from melting to freeze up, but it's intermittent, sporadic type of pulsing of the melt and freeze, becoming more and more freeze up. Next. One last topic I'm involved in looking at is we're looking at an Arctic boundary layer paradigm that involves a number of key structural features in the Arctic boundary layer. This Arctic inversion, which we believe is, or are hypothesizing is a general large-scale inversion that forms of the Arctic ice and snow-covered regions, and that this forms the general interface between to the free troposphere, and everything below is affected by the sea ice at various scales. The more classical atmospheric boundary layer is much shallower, is down 30 to 200 meters or so, and this is where you have it may be stable, maybe an inversion, or it can even be surface force mixed layer. And we also have these cloud mixed layers that were also mentioned earlier that are produced by long wave radiated cooling at cloud top, particularly on stratus clouds that are within this Arctic inversion. And they can sometimes couple with this atmospheric boundary layer near the surface, the surface mixed layer. Also important are these low level jets that are throughout this lower atmosphere in the Arctic, and they enhance the vertical mixing also. And so this is a study of where, when, and how these features occur and how they vary and interact to induce the vertical mixing throughout the annual cycle. So I'll leave that alone.
Good, all right, and then I'll give a couple slides to bring us home here. So a lot of my work over the years is focused on Arctic clouds. And so one way to think about Arctic cloudiness is within the context of the Arctic, there's kind of this bimodal state. And the bimodal state, we've already heard about it some here, is kind of defined by the long wave radiation. So if you have, so for example, here in the black line, there's a distribution of net long wave radiation at the surface. This is at Mosaic, but it's kind of the same almost anywhere you go in the Arctic. You see this really clear bimodality, two things happening in the Arctic. One is a case where you don't have a thick atmosphere, you don't have clouds. So you have a large negative long wave net, surface is cooling to space. The other mode is right near zero long wave net. This is an opaque atmosphere that's in radiative equilibrium with the surface. Right, so these two different states are really important. You can see the difference between them is something on the order of 40, 50, 60 watts per meter squared. That's a big energy difference. So what determines these two states? It drives cloud fraction, for example, and it drives the overall energy balance at the surface. And so this figure is just kind of showing some of the details. I've kind of partitioned up these bimodal states in a number of different ways to really understand what's driving those. For example, here, the different color codes are showing the liquid water path, how much liquid water is in the atmosphere, kind of colored onto these bimodal states. And you can see that a lot of this cloudy state, well, it's got a lot of liquid water in it. So that's really important. And this semi-transparent state doesn't have much liquid water. Although sometimes in the blue case here, there's not liquid water in this opaque state. So these are just really thick ice clouds. But you can also have ice clouds over in this state where they're not really doing much radiatively. So it's really important for us to understand the liquid water and the ice, the phase partitioning between those. As we saw from Amy, it's really hard for models to do that. I'll carry on. So then taking those two different states, you can imagine these great measurements we had at Mosaic of measuring the surface energy budget, all the different terms, radiation, turbulence, conductive heat flux, you've heard about them from the other presenters today. Take all those terms and separate into the cases where you have this semi-transparent state and then this opaque state, right? Kind of clear sky and cloudy sky. And so that's kind of what's shown in these two figures on the left. All the energy budget terms, you've got the short wave net radiation at the surface in red, long wave in blue, there's conductive heat flux, sensible heat flux, and latent heat flux below that. So on the top is the semi-transparent state, on the bottom is the opaque state, and there's some big differences there. If you just take the difference between those, it's kind of like a cloud forcing. So we hear a lot about cloud radiative forcing, but how about cloud forcing of everything else? And that's kind of what I'm interested in, is putting together the whole energetic picture of if you have one state or the other, how does the whole system adjust to that large radiative forcing driven by clouds? And so that's kind of what's on the right here. This is the cloud forcing of all these different parameters over the course of the whole year at Mosaic and how they vary So a couple key features in the top panel on the right, you see in the long wave, there's a positive value, right? Clouds blanket the surface, they warm the surface. We know that pretty well. In the short wave in the red, well, they cool the surface, they shade the surface. And of course, there's no sun to shade in the wintertime, right? So this radiative balance is changing over the course of the year. And we also see in the sensible latent and conductive heat fluxes, some changes as well that respond to this cloud state. For example, in the conduction that, Anne was looking at, if you bring a cloud in, it warms the surface, it decreases the gradient between the surface and the warm ocean below, decreasing the gradient, so it decreases the conductive heat flux upwards, which could have implications for ice growth, for example. And many other things. It's kind of interesting in the summer, as the surface starts to melt, the skin temperature becomes insensitive to clouds or no clouds, because it's just going to be melting anyway. So all these terms that are kind of dependent on the surface temperature kind of become really insensitive. So it's more of a radiatively driven summer and a kind of a balance of other terms in the winter. I've done a similar kind of analysis. I'm not going to go into many details, but this is for coastal Alaska. This is actually based on 10 years of data. Again, looking at all these different energy budget terms and the cloud impact on those terms. It's a different story there, right? In Alaska, there's snow in the wintertime, and then the snow melts and exposes relatively dark tundra, right? So the albedo change is really important, and it shifts the balance between the long wave and the short wave cloud effects on the surface. And that has really interesting implications for things like, down at the bottom is the kind of subsurface soil fluxes, right? The effect that clouds and these kind of cloudy states can have on permafrost melt, for example. So really nice analysis there. And my last slide is jumping back to the mosaic data. And this is kind of interesting. If you take the surface energy budget, like we've heard from others here, and you add up all the different terms, but when you get to the melting point, there's some excess energy, and that energy goes into actually melting of snow and sea ice. And that would be something you really want to know about if you're interested in the fate of the sea ice, right? So if you take all the times when the temperature is at the melting point, you look at that excess energy, that's what I'm calling the energy for melt. In reality, a little bit of that energy might penetrate all the way through the ice into the upper ocean, which also kind of contributes to melt in the long run by warming the ocean. In any case, what I've plotted here, all these little points here are the energy that's available for melt of the sea ice as a function of the cloud liquid water path. And then I kind of bended up and did some statistics there, box and whiskers. And what you find is that the energy that's available for melt is maximized when you have thin liquid water clouds, right? So it's maximized here with clouds with a little bit of liquid water, but not too much. If you get a lot of liquid water, really thick clouds, you actually get less available energy for melt. This is a similar result we found over the Greenland Ice Sheet. So that's kind of interesting, and that's kind of ongoing work to quantify that a little more. But I think that's all that I have. So I just wanted to summarize for all of us. I think you've seen really a wealth of expertise in our team. We really cover a lot of range with field work, observations, data analysis, using big data sets, developing models, evaluating models, and all that's kind of loosely related to the cryosphere and atmospheric processes in the Arctic in some way. So lots of nice connections to NSIDC. I didn't really add this one up, but collectively we have something like 125 years of polar research experience. That's a lot in our team. Heavily dominated by a couple of these old guys. But, anyhow, and we're really looking forward to building more connections with you all at NSIDC. So we'll open it up for any questions that people have. And I think there are some online.